All right, what do you have for number 20?
Sine dy dx equals sine x minus y.
Okay. And switch screen. Okay. So what are we doing here? What's my substitution? What type is this? It's linear. So what are we going to make our u? Yeah, we're going to take our u and make it x minus y. That means that du dx equals 1 minus dy dx. So dy dx equals 1 minus du dx. And I do that because I've got to sub in for dy dx. So here's my dy dx, and I already know what x minus y is, okay? So if we substitute those in, then this becomes 1 minus du dx equals the sine of u. All right, now what do we do next? Let's see. We are going to subtract 1, divide by -1. So du over dx equals 1 minus sine of u. I don't know why I wrote that. Yeah. Okay. Then this is separable, yes? So I'm going to multiply by dx, divide by 1 minus sine of u. And we're going to integrate that. I'm guessing this is where we got stuck. Okay, what do we do? Thoughts, ideas?
I thought it looked something similar to a tree.
Okay. It's got a sign in it, so it's probably going to be something involving a trig integral. How do we get ourselves out of this situation? What'd you say? Move on to the next problem. What identity would you use?
Square.
I wouldn't, but I know where you're going with that. Okay, so what's another way that we can make the denominator 1 minus sine u? There we go, there we go. Use the conjugate, right? Or the same idea. What does that do for us? Okay, so then we would have a 1 plus sine u on the top and a 1 minus sine squared u on the bottom, yes? The right's just going to be an x plus c, whatever we get. Now, the whole point of going 1 minus sine squared would be to do what? Change it to a cosine, okay? So let's do that. Okay, now usually we would then sub for the bottom, right? For something in the bottom. So you would want to sub for cosine. And the derivative is sine, which is kind of there, but there's also a +1 in the way. So I should probably do something else first. So what I'm going to go ahead and do is I'm going to divide through. So this will become 1 over cosine squared u plus the sine u over cosine squared u du. One over cosine is the same as, yeah, so this becomes secant squared u plus the sine u over cosine squared u du. Antiderivative of secant squared. Tangent, so this one's tangent u. Now I've got to integrate. Let me distribute my integration here. There we go. What do I do with that second one? Now we're gonna use sub, so, but we're already using u, so let's use v. Let's let v be cosine of u. Then dv is negative sine u, du. And so that will become the integral of negative dv over v squared. Then I get the tangent of u, which we had. Let's see, antiderivative of negative 1 over v squared would be positive 1 over v. But v is cosine. So it becomes the tangent of u plus the secant of u equals x plus c. And then the last piece is to sub back in. So our u was what, x minus y? All the way at the top, yeah, x minus y. So this will become the tangent of x minus y plus the secant of x minus y is x plus c. So yeah, the integration on that one's a bit tricky. Yeah, really. Yeah. What's 22?
dy over dx minus y equals e to the 2x over y.
Like that? Okay. All right, what type of substitution are we going with here? Bernoulli's, because it looks kind of linear except for this y cubed, right? So that means that this is Bernoulli's, and we're gonna make our u equal to what? Y to the 1 minus whatever our power is, right? So 1 minus 3. So this becomes y to the negative 2. Let's see. That means du dy is negative 2y to the negative 3. The derivative with respect to y. And remember that when we find dy dx, that's the same as dy du times du dx. And so that means our dy dx is negative 2y to the negative 3 du dx. Also be a little bit careful here, because if I'm going to solve for y up here, my y is equal, u is equal to y to the 1 to the negative 2. So to get rid of that exponent, I've got to raise both sides to what power? Negative what? If I want to go from a y to the negative 2 to just a plain old y, I want to make that exponent 1. What do I multiply negative 2 by to make it 1? No. Here's what you got. Yeah. It's going to be negative 1/2. Why? Because you have u equals y to the negative 2, which is the same as u equals 1 over y squared, right? So if you take the reciprocal of both sides, that'll give you 1 over u equals y squared. And then you would have to take the square root, right? So that would be y equals 1 over u to the 1/2. And that's the same as u to the negative 1/2. The other way to think of it is this way. So I had u equals y to the negative 2. I've got to raise both sides to some power in order to make this a y, right? So what number times 2 will give me that? Well, negative 1/2, if I multiply it on both sides, will reduce down to 1. And so I end up with u to the negative 1/2. Okay, so watch out for that. Yeah.
You're doing the dy over du. Is that the same as du?
I know, and now as you said, I'm like, oops, I did it backwards. I need to do, instead of differentiating up here, I need dy du. I gave you du dy, right? So now that we're solved for y, So we have y equals u to the negative 1/2. So then dy du is negative 1/2 u to the negative 3/2. And that's what I substitute in up there. So this goes here. So negative 1/2 u to the negative 3/2. I would have figured that out in a second because it wouldn't have worked when we plugged it in, right? So it should work and come out nicely when you do this. So that means we have the following substitutions. We know that here is our dy dx, right? It's the derivative of u, not y. And then this is our y. So dy dx is 1/2 u to the negative 3/2 du dx. And y is u to the negative 1/2. Everybody clear on how I got those? Because I didn't get it right the first time. So if you need to see it again, I can do it. Okay. All right. So I'm going to plug that back in here. So that means that my dy dx is now negative 1/2 u to the negative 3/2 du dx. Minus y is u to the negative 1/2. Over here, we have e to the 2x. If y is u to the negative 1/2 and we cube it, that will become u to the negative 3/2. Hold on. This is all a little congested. Let me move it out of the way. There we go. Okay. Now that I have the substitution done, in order to simplify, we're going to multiply to get rid of to make what's in front of the du dx 1. So to get rid of the negative 1/2, I'd multiply by negative 2. To get rid of the u to the negative 3/2, I'm going to multiply by u to the positive 3/2. When I do that, that cancels everything in front of my du dx. So now du dx is a coefficient of 1. Distribute that to the middle. So negative 1 times negative 2 is positive 2. Add my exponents on the u. So negative 1/2 and 3/2 becomes u to the 1. So just plain old u. And then on the right-hand side, the u's will cancel, but I'm left with the negative 2 times the e to the 2x. From here, this is linear. So we're starting a whole new problem. This one's linear. So we need the integrating factor. The integrating factor is e to the integral of what's sitting in front of the u. So that's a 2 dx. So my integrating factor is e to the 2x. Multiply that through. Regroup the left-hand side. That's e to the 2x times u, everything prime. Negative 2 e to the 4x on the right. Go ahead and integrate each side. That leaves me with e to the 2x times u on the left. And negative 2 over 4 e to the 4x plus a constant on the right. Go ahead and divide through by e to the 2x. That's going to give us u equals negative 1/2 e to the 2x plus c e to the negative 2x. Last thing, let's go ahead and substitute for our u. Our u is 1 over y squared. And I'm okay with leaving it like that because I'm not going to end up solving for y anyway. If you want to take the reciprocal, you can. I lost a negative. There you go. But I would leave it like that.
The y cube. Let's figure out cube.
How did I get the u? Right from here?
No. Something the y cube. How'd you get
Okay. So I'm looking for y cubed, right? In terms of u. Y is u to the negative 1/2. And we cube it. So you're going to multiply your exponents to get u to the negative 3/2. This one's a big exercise in exponents. It gets a little tricky. Yeah.
So I guess 2 questions. Is it okay if we use different letters for the substitution variables?
Sure.
Because essentially, when I was doing the homework, I kind of reviewed it via the book, and the book doesn't like a slightly different way.
That's interesting, but okay. Doesn't bother me one bit. Whatever letter you use is fine.
Because it is a slightly different technique as well.
Shouldn't be. Not for Bernoulli's anyway.
Well, the way in the book, at least the way I managed to do it is the first step is you multiply by the inverse exponent. So you take that equation and multiply everything by y to the negative 3.
Okay.
And then that will leave your kind of middle thing, but in this case, the negative y. They'll leave it y to the negative 2.
Correct.
And so when you substitute that in for u, like everything.
Right. But that's exactly what we did.
Yeah. So like
Yeah.
I get there in the end.
Well, you're just doing more work to get to the substitution. So they're probably showing you some kind of structure as to where that substitution comes from, right? But assuming that this has the same structure, right? This always is a y to the first power. So if you're going to divide by whatever this is, you're always going to get whatever this will become y to the current power, which is 1, minus whatever this power is, which is the 3, which is the substitution that we gave.
Is it okay if I do it?
I mean, that's fine. You're just doing extra steps to derive what your substitution is. So if you're okay with that, that makes you happy. I'm totally fine with that too. But just to be clear, it is the same procedure. Yeah. Mm-hmm. We just skip that and say, yes, we can see that once. And we know that because in general, that's the n, right? So that's where they get that your substitution is y to the 1 minus whatever that power is. I just didn't go through all the details on how and why and all that kind of stuff. Sometimes it's worth it to go through the how and the why, and other times it's just not. But if you like it, then go for it.
I was at least for the time, I think, because I didn't have to deal with that like negative 3/2 thing.
I see what you're saying. I feel like you still do, but we'll let that one go. But yeah, all right. Everybody okay with that? Other questions? Yeah. Okay, what's 24?
dy over dx plus y over x minus 2 equals 5 times x minus 2 y to the 1.
On that? Okay. All right. Your n here for Bernoulli's is going to be what? 1/2, right? Okay. So that means that your u substitution is going to be y to the 1 minus that 1/2. And that's going to be y to the negative 1/2. Then let's go ahead and solve for y. If we do that, we raise this to a -2 power. That will get me y equals u to the -2. Yes, ma'am. Oh, yes, it is. That makes it better. Then we only need a +2 to balance. So if u is square root of y, then y is u squared. Then dy du is 2u. And that makes your dy dx 2u times du dx. And so here are your two pieces that we're plugging in. Okay, if we go ahead and plug those in, this becomes 2u du dx. Let's see, plus. I'm going to write it as 1 over x minus 2 times u squared equals 5 times x minus 2. And y to the 1/2 was our u. Then I'm going to get rid of what's in front of the du dx, but I'm multiplying by 1 over 2u. That will leave me with du dx plus 1/2 1 over x minus 2 times u. And 5/2 times x minus 2. Okay, from here, this is now linear. So my integrating factor is e to the integral of 1/2 1 over x minus 2 dx. So that is e to the 1/2 ln absolute value of x minus 2. We put the 1/2 up, the e and the ln cancel, so that is x minus 2 to the 1/2. Yeah, Andrew. From where?
For substitution.
You good? Okay. I was anticipating negatives as well. Turns out it's positive. All right. Multiply that through. That becomes x minus 2 to the 1/2 du dx plus 1/2. That'll be x minus 2 to the negative 1/2 u. So you got a 1/2 on top and a 1 on the bottom. The 1/2 will cancel and you'll still have a 1/2 power on the bottom. On the right, that's 5/2 times x minus 2, and you're adding exponents this time, so it'll be 3/2. So therefore, what's on the left can be rewritten as x minus 2 to the 1/2 times u everything prime. And the right-hand side stay the same. And we can go ahead and integrate with respect to x. let's see, that'll leave us with x minus 2 to the 1/2 times u on the left. On the right, I'm going to treat that x minus 2 as one quantity. So to integrate, I'm going to raise the power to 5/2 and divide by 5/2, but that's just going to cancel out the 5/2 that's in front. So the antiderivative is just that. Add my constant. To solve for u, I'm just going to multiply through by x minus 2 to the negative 1/2, or think about dividing by that to the 1/2. That'll give me u equals, let's see, x minus 2, when you subtract a half from 5/2, that's 4/2, so x minus 2 quantity squared. And you'll have plus c times x minus 2 to the negative 1/2. And then we sub back in for u. U was y to the 1/2. I'm not going to solve for y because that would mean squaring all of that. I mean, I can write it out, but it's going to look just as messy as it does now. So no benefit to going to y equals. Yeah.
So in the notes for Bernoulli,
Yes.
I have written down that n had to be greater than or equal to 2.
We started, really what you want is n is not equal to 1. Okay, so it works for anything. And I wrote that down, but I also then mentioned that for now we're going to look at that, and then we can also add in some fractional ones. So it does work for fractional exponents. Yes.
I have a question on,
Yeah.
So I was reviewing
Mhm.
last night this morning.
Yeah.
And I found this video like having a year with finding view like if he did so he did like his integrating factor was e to the integral of 1 minus n p of x dx. And then yeah, you have the general form of the Bernoulli's equation. And then he did y to the 1 minus n equals 1 over the integrating factor.
Okay, hold on one second. Let me trace through where you're coming from. Well, what's happening is you're skipping procedure for a formula. That's what you're doing. So instead of getting it into the right form and doing the right things and solving it all the way through, he's essentially saying, well, you can skip all of this beginning part by just memorizing that this is the form of what the integrating factor should be, right? And so it kind of like, so yes, it's going to work. Yeah, and we can do that for every type of equation, but then all you're doing is memorizing forms of solutions, right? Yeah, you're just playing plug and play. So pretty much, yeah. So yes, he's definitely not wrong about what he's doing, and this is 100% correct. Without going through, I'm sure, based on what you're writing, I'm sure that that's just, he's just organizing it and giving you a generic form, right? Which is what I didn't do. And there is value in that because it is quick and easy, right? But what I'm trying to get you to do is work to develop a sense of, I'm starting this with this equation, I'm going to do something so that I get a new equation, and then I look at that one and say, how do I solve this, right? As opposed to just, I have a bunch of formulas that'll get me to the end. So I'm trying to build a structure for which we tackle differential equations. Does that make sense? Would I be upset if you memorized and used the formula? No, as long as you can somewhat justify and give me enough steps to show that, like, I know what this is and I know why it works. But I also want you to be able to go through the entire process, right? Because there is, I know it's long, I know some of it's tedious. There is a method to that. Like, I'm trying to build your resilience to some of these things, right? Because as we move forward, they won't get shorter. You know what I mean? Okay. And so I want you to kind of develop that structure and process in addition to, here's a formula and how I get my answer, right? So I'm okay with using a formula in the short term, but in the long term, I want you to be working towards that. Make sense? But yes, there are absolutely ways that you can develop, like the same thing happens with the integrating factor for linear equations. Like I could have just like plopped down, here's the formula, right? And I could have shown you where it comes from. In fact, I did show you where it comes from, but I don't think it's good strategy and good pedagogy in the long term to have you just memorizing formulas, right? That's a discussion in the teaching of differential equations about how do you make it not just memorize, plug and play, right? So we're trying to build kind of a framework from which you can always work from. Does that make sense? Okay. But yeah, these are a lot, I'm not gonna lie, right? And the detail to get there, you know, you have to be able to say, okay, now I got that far, now I breathe and we go again, right? Because you're doing multiple problems, because essentially right here is a problem that I was on the, would have been on the last test, right? Like an entire problem on the last test. And now that's a sub problem in a larger problem, you know, that we're working towards. So that's the kind of the way differential equations work, in that a lot of times we have to do some sort of substitution that changes our differential equation into a different format. So then we can do something else with it, right? It's not always a direct, like, here's how I get the answer. And that's what I'm trying to like show you repeatedly, right? We make some sort of substitution. For example, when I did my research, when I'm working with big differential integral equations, so things that have derivatives and integrals in them and how you balance all of that, making certain substitutions so that it looks different, right? So now I can use this technique, and now it looks different, so I can do these techniques. So that kind of ability to transform differential equations is a kind of like an overarching strategy. Okay. So that's kind of where this is coming from for me. All right. We are just about out of time. So what we're gonna do is we're gonna table both the homework and the quiz for Monday. So that way you can take this home that we've gone over some of these. I want you to make sure you clean them up. I highly suggest, knowing what's on the quiz, that you go back, especially some of the ones we went over. If you didn't get those the first try, go through and write them down in detail. Make sure that you can do those using mine as a help, so that when we come in on Monday, we can jump in and ace that quiz. Okay? I feel like that would be a better use of our time. Yeah, Chip. They are. I can at the request. Sure thing. It's a bit. I'm not gonna lie. Yeah. And I'm not gonna lie, as soon as, like the one I did in class, when you do it with a -1, it's not as bad because all you're working with is -1. As soon as that becomes something that's not a -1, now you're working with fractional powers here, and that adds a whole level of complexity to it that, you know, doesn't sound like it should be a lot, but it's just an extra thing to manage, right? So I 100% get that. Totally on it. So yeah, I will, I'll upload some Zoom lectures from some recordings. Yeah.